Hello, I'm Taufik Kamaloye at the Department of Aeronautics and Astronautics, Faculty of Engineering, Kwara State University, Malete, and this is the Harmattan semester of the 2020 and 2021 session. The class is AAE321, that is Incompressible Aerodynamics, and my email address is there. The class date and time are as they are on the Faculty of Engineering timetable, and the course description is just here. The hope is that the course will introduce the fundamental principles of aerodynamics to the student and get them familiarized with the terms and vocabularies that are used in the field of aerodynamics. It's also the hope that the course will demonstrate to the students the basic application of the conservation laws and thermodynamic principles to engineering problems which involve the flow of fluids. And the aim is to lay the theoretical foundation for the students to solve simple engineering problems in aerodynamics, and also provide the basic understanding that is required for advanced studies in aerodynamics. And the mode of the lecture is through PowerPoint slide presentation. The hope is that the slides, soft copies of the slides will be made available to the students prior to the class. When that is the case, the student is advised to read ahead of the class, and also the student is also advised to take the habit of taking notes during lectures. For a 2-hour class, there is going to be a break of 5 minutes in between the hours. The textbooks that will be used for this class are majorly the one that will be used is the Fundamentals of Aerodynamics by John D. Anderson. Additional references will also be made to Aerodynamics for Engineers by these authors, Bertens and Cummins. The assessment method will be based on attendance, continuous assessment work, computer projects when possible, and also the final exam. It is a hope that the students will strictly adhere to FAIR principles that include originality, sincerity, and promptness in those assessment work. The grades will be broken down in this manner. There's going to be 5% for attendance, 10% for homework, 15% for continuous assessment tests, and then 70% for the final exam. And this is the mode in which the grades will be determined. 70 to 100% will be classified as A, 60 to 69% as B, 50 to 59% as C, and D 40 to 49%. Below 40% is F. Actually, I think I need to update this because as per the university-wide rule, I think F starts from 45, below 45. So I need to update this. Anyways, the course outline is as follows. We'll be looking at the fundamental principles of aerodynamics, and under that we'll look at topics. Like I said, the reference text is majorly fundamentals of aerodynamics. So the course outline has been drawn based on the chapters of fundamentals of aerodynamics. So in the first chapter, we'll be looking at the introduction to aerodynamics, dimensional analysis, and flow similarity, and then we jump to chapter 2. We'll look at the conservation equations and fundamental principles. That is the continuity equation, which is based on the conservation of mass. the momentum equation based on the conservation of momentum, and the energy equation, which is based on the conservation of energy. We'll then also look at the different frames of reference that can be used to study fluid flows. We'll look at the Eulerian frame of reference and the Lagrangian frame of reference. We'll look at the vorticity and rate of strain, circulation, velocity, potential, and stream functions. Then we'll proceed to chapter 3, where we'll be looking at some part of inviscid incompressible flows. There we'll discuss Bernoulli's equation, Laplace's equation, and fundamental solutions for two-dimensional potential flows. We'll look at elementary flows, and then we'll also discuss Kotar-Joukowski theorem. Then we'll proceed to look at flow over airfoils. We'll discuss the Kotar condition. We'll look at Kelvin's circulation theorem, and then we'll model flows over airfoils. We'll look at Joukowski airfoil, and then we'll discuss the thin airfoil theory, finite wings, and Prandtl lifting line theory. And this will be in chapters 4 and 5. And then we'll try to also discuss at the latter part of the course. We'll try to have some discussion on viscous flows. That is, we'll go to chapter 15 and look at viscosity and thermal conductivity. And then we'll look at the stress relation for a Newtonian fluid. We'll familiarize ourselves with the Navier-Stokes equations and dynamic similarity. And then we'll also go to chapter 16 and look at simple exact solutions of the Navier-Stokes equation, that is the Couette and Poiseuille flows. We'll also jump back a bit to chapter 15 and also continue this discussion. Jump back a little bit to chapter 15 to start a discussion on the boundary layers, but then we'll go back to chapter 19 to finish the discussion on boundary layers. At the end of the class, it is the hope that the students will have learned to calculate aerodynamic forces and moments from pressure and shear stress distributions on airfoils, and also calculate lift for an arbitrary airfoil using panel methods. Part of the intended learning outcomes is that the students will be able to determine loading on a wing and apply laws of dynamic similarity in its use of wind tunnel data. It is also the hope that the student will be able to apply the continuity and momentum equations to simple engineering problems, and also apply the incompressible equations to solve flow problems, as well as that the students will be able to analyze nozzle flows. So then we begin with the slides on the fundamentals of aerodynamics. These slides are based on the 4th edition of the book, and the slides were made by Liang Jie, and they were sourced from the internet. So this is the name of the person who put the slides together. Any version of the textbook should be from the 4th edition, or from the 2nd edition should be okay for this class. So we proceed, and this is the picture of John D. Anderson. As we discussed from the outline, we're going to be looking at some introductory thoughts, and we look at some basic definitions of basic aerodynamic quantities, that is the pressure, density, temperature, flow velocity, and streamlines. And then we'll proceed to look at the source of aerodynamic forces and moments, and how to obtain them from integration of surface properties. and this is just a way to start looking at practical applications of aerodynamics. And then we proceed to definition of lift, drag, and moment coefficients, which are some of the most frequently used terms in aerodynamics. And then we also proceed to defining what the center of pressure is, and the center of pressure is where the aerodynamic forces act on the body. And then we proceed to looking at dimensional analysis and flow similarity. These are very powerful tools to define governing parameters in aerodynamics, and these are the basis on which wind tunnel testing lies. And then we look at what happens when there is no flow. What happens in a fluid when there is no flow, that is fluid statics. And then we'll proceed to look at the different types of flows, what continuum flow mean, what are inviscid and viscous flows, what are incompressible and compressible flows, subsonic flows, transonic flows, supersonic flows, and hypersonic flows. That is essentially we look at how we look at the subdivisions and categories in aerodynamics, and then we proceed to start looking at some viscous part of aerodynamics. That is, we look at the boundary layer and try to look at how friction is accounted for in the flow of fluids. So that's just a roadmap for this slide. To begin with the fundamental aerodynamic variables, it will be instructive to first also define what aerodynamics is. Aerodynamics is the study of interaction of flow of air about a body, and as we know, dynamics is a branch of mechanics that deals with the motion of bodies under the action of forces. We should also know that statics deals with the action of forces on bodies at rest. And of course, dynamics can also be subdivided into two categories, that is kinematics and kinetics. Kinematics, which is the study of motion without reference to the forces which cause the motion, and kinetics is the it relates the action of the forces on bodies to their resulting motion. So those are just some basic definitions that are instructive to be remembered before we proceed. Some of the most basic variables in aerodynamics are pressure, density, temperature, flow velocity. I'm sure we are quite familiar with these terms, but we just also need to have some technical, however basic, definitions of these terms as they relate to aerodynamics. The pressure is the normal force per unit area that is exerted on a surface due to the time rate of change of momentum of the gas molecules which are impacting on that surface or crossing that surface. That is, if you have an elemental area dA at B, and then there is some elemental force dF on the side of the A due to pressure, then the pressure is defined as the limiting case of dF dA as the area dA tends towards 0. So that is the definition of pressure. And then we proceed to defining and also pressure is usually defined at a point in the fluid or at a point on a solid surface. Pressure is also a point property That is, it varies from point to point within the fluid. Then we proceed to look at density, and density is just the mass per unit volume. That is, if you have an elemental volume around a point B in the fluid, that is denoted by dV, and the mass of the fluid inside dV is given by dm. Then the density, which is usually denoted by rho, the Greek letter rho, is equal to the limiting case of dm over dv, that is, as dv tends to 0. The temperature plays a very important role in high-speed aerodynamics, and it is just used to define the kinetic energy in this expression here. That is, the kinetic energy is equal to 3/2 times kappa T, where T here is the temperature and kappa is the Boltzmann constant. So the temperature of a fluid is directly related to its kinetic energy. And then we proceed to also look at the flow velocity. The flow velocity is, or the velocity of a flowing gas at any fixed point in space, is just the velocity of an infinitesimally small fluid element as it sweeps through that point in space. So, for instance, here, this fluid element that is flowing in this fluid, as it flows through point B, whatever velocity that it has is just considered as the flow velocity. And then we also look at what is called the shear stress. So here, looking at this figure, we have two streamlines, and we'll also be defining what streamlines are and some subsequent slides, but for now we just consider two streamlines. On this streamline, the flow velocity is v, and just above it, the flow velocity is slightly higher, and it's v plus dv. Because of the difference in flow velocity, there is some velocity gradient which gives rise to some friction between the streamlines, and where there is friction, there is also shear stress. So then the shear stress is equal to the limiting case of the F, that is the frictional force, over the an elemental area, dA, as dA tends to 0, and the shear stress is experienced tangentially along the streamline. The shear stress for the kind of fluids and gases that we'll be talking about here in the incompressible aerodynamics, the shear stress is directly proportional to the velocity gradient, and the constant of proportionality is called mu, which is the coefficient of viscosity. Actually, mu is not really a constant because it is a function of the temperature of the fluid, but for low speed aerodynamics, such as the ones we'll be talking about majorly in this class, mu can be taken as a constant. And then we proceed to look at the aerodynamic forces and moments on a body. The basic source of these forces and moments on a body are the pressure distribution over the entire surface of the body, and also the shear stress distribution over the entire surface of the body. Recall that whilst we were defining pressure and shear stress, we said they were for the pressure it was the normal force per unit area, and shear stress is the normal tangential force per unit area. So that means if you have the distribution of such pressure and such shear stress over the surface, we can try to integrate such distributions to get the force on that body and the moment on that body. And that is just what we'll be doing in the latter part of the course. Like I said, the pressure acts normal to the surface. That is, it acts perpendicular to the surface at any point in time. So at this position here, the pressure is acting perpendicular to the surface there. At another point here, it will be acting perpendicular to the surface. At another point here, it will also be perpendicular to the surface, the local surface there. The shear stress, which is denoted as tau, however in this slide here it's denoted by T, acts tangentially to the surface. It's always tangential to the surface. So here the pressure and the shear stress are functions of S, where S is a measure of the distance along the body surface. So at any position on the body surface, the pressure may be different and the shear stress may be different. So when we integrate the pressure all around the surface and also the shear stress all around the surface, we get a resultant aerodynamic force R and a resultant aerodynamic moment M. So that is what we are interested in doing in aerodynamics, how to go from using the knowledge of the pressure distribution and shear stress distribution to get the resultant force on the body and the resultant moment on the body. Here the body which has been drawn is just the cross section of a wing, which is an aerofoil. Later on we'll also discuss what aerofoils are, but for now they're just the cross section of a wing. And here this arrow denotes the flow, that it shows that the flow is coming from this region of the figure, and V infinity is just the free stream velocity, as we are going to be seeing in the subsequent slides. So V infinity is the relative wing, and it defines the flow velocity far ahead of the body, that is the free stream velocity. So the resultant force can be resolved into components. When it is resolved into a component that is perpendicular to the flow velocity, then we have the lift, and the resultant of R and parallel to the flow direction is the drag. The resultant of the force perpendicular to the to C, this line here of the aerofoil, is called the normal force, and that which is parallel to that line is, when it is resolved into when R is resolved into the component of R in the direction of this line C is the axial force. Also the angle of attack is the angle of inclination of line C with respect to the flow velocity line, so, or the flow direction. So the angle of attack is defined as that. From this figure here, we can also find expressions that relate the lift, geometrical expressions that relate the lift to the normal force and the axial force using the angle of attack. A similar expression can also be derived for the drag. This quite simple to derive, and the student is advised to go through the algebra. In the next lectures, we'll look at the details of how to get the lift and the drag expressions from the integration of pressure and the pressure distribution and the shear stress distribution on an arbitrary body.